Angular displacement is the angle turned through by an object in circular motion. So here we have a spinning circle of radius r, and I've marked out one of the radii on it so we can see what happens as this rotates. As it rotates, the line is going to move from one location to the other, and that angle is the angular displacement. We symbolize it delta theta. The delta s is the arc length, which is the linear distance that is traversed there. Our first equation in angular kinematics is the arc length is equal to the angular displacement times the radius. And this little two-headed arrow is my notation that we have an arc length that is rotating, or an angular displacement that is rotating. Delta S is the arc length, which we measure in meters. Delta theta is the angular displacement, which we measure in radians. You can see here, if I mark out two specific spots on this radius, I'll mark one with a circle and I'll mark another with a square. When these rotate, you can see that the square has traveled a bigger arc length. The circle has traveled a smaller arc length, but they have both gone through the same angular displacement. The difference is the circle has a smaller distance. There is in effect a smaller radius to the circle and a larger radius to the square. The angular displacement delta theta of any part or all of a rotating object is everywhere the same. This will apply for other quantities like angular velocity and angular acceleration too, but we can say this: the circle here to here undergoes a certain angular displacement. The square undergoes that same angular displacement. This whole object undergoes that same angular displacement. That's what we're trying to say statement here at the bottom of the screen. In case you don't know what a radian is, let's make sure we clear that up. A radian is the angle subtended by an arc that is the same length as the circle's radius. Let's say I cut a piece of green string and I lay it along the radius there. Now I'm going to take two other green strings that are equal in length to this one, and I'm going to pick one of them up and I'm going to lay it right here, and I'm going to start wrapping it around the circle. Then I'm going to take this last green string and I'm going to connect those to form a pie shape. That right there is 1 radian. That's what we mean by a radian, that it is the angle subtended by an arc that has the same length as the circle's radius. A radian is a little less than 60 degrees. It's about 57.3 degrees. 2 pi of those, in other words 6.28 something of those, would take you all the way around a circle. Those are some equalities that you would want to memorize. 2 pi radians is 360 degrees, or pi radians is 180 degrees. And you're probably familiar with that from taking your algebra or algebra 2 class. Pi over 6 radians, pi over 3 radians, and so on. Around the circle all the way is 2 pi radians. Right there, if you can see in that picture, right there is 1 radian. You can see that 60 degrees is slightly more than 1 radian. See this thing that I'm circling here with my laser pointer? Pi is 3.14 something. Well, 3.14 divided by 3 is slightly bigger than 1 radian. So 1 radian is not quite 60, something like 57.3. Final thoughts on angular displacement. Angular displacement delta theta is the angle that an object in circular motion turns through. In the SI system, delta theta is measured in radians. 2 pi, or about 6.28 radians, are equivalent to 360 degrees, one time around a circle. Something that is a distance r away from the axis of rotation will move through an arc length, i.e. a linear distance, given by this equation in yellow, which says that the arc length is equal to the angular displacement times the distance that the point in consideration is from the center. That's what r is. All points on a rotating body experience an identical angular displacement delta theta in a given time interval.